Alright, thanks for checking out Six Sigma Tool Guide. Today we're going to take just about 10 or 15 minutes and talk about the histogram. That is a specific type of bar chart. Very powerful tool. It's very helpful for understanding data, and it gives you a good sense of how a process functions, and it helps you avoid something I call the average problem, and we'll talk a bit about that as well. So alright, buckle up and let's get started. So what and why? What is a histogram? A histogram is really just a bar chart. There are a couple specifications that make it a histogram. Its purpose is to give you insight on the process that's being examined, and we're going to pay particular attention to variance, something measured in standard deviation, but variance, we're going to use that word a lot when we talk about a histogram. The data is going to be grouped in buckets. These buckets are typically connected or arranged in some meaningful way. Typically it's a count of instances, that's what we're measuring. And the data usually is continuous data, things like time, height, money, that sort of thing. And we're going to pay a lot of attention to the shape of the histogram because that's going to tell us a story about the process. So that's the high level. We're going to get into some visual aids that demonstrate each of these points next. Okay, here are those visual aids I mentioned. As I said, the data is going to be grouped in buckets. And as you can see there, the red arrow pointing to these bins of 100 to 150, 150 to 200, 200 to 250, etc. And notice that those buckets are connected. They're sort of ranged. It makes sense that we have a bucket that's 100 to 150, and then the next bucket next to it is 150 to 200. So we can pretend those are weights, and we're measuring how many things, weigh somewhere between 100 and 150 pounds, how many weigh between 150 and 200 pounds. That's different than on the left where we have categories, like USA, India, UK, New Zealand. There's no natural connection between those countries. There's nothing that connects USA to India except land and sea. But it's not like the ranges we have on the right where it makes perfect sense to have them arranged the way we do. This is going to be a count. You're typically going to be counting things that fall within, counting instances that fall within those bucket ranges. And normally the data is going to be continuous data, often time, height, money, length, those sorts of things are going to be what we're measuring. So variance, we're going to talk a lot about variance. Standard deviation is something that we measure variance with. We're not going to get into the calculation of standard deviation in part one. We're just going to really kind of talk about variance and what it is. And when we use that word, try and think of this slide. I want you to remember Bill and Jill. Bill and Jill both have lemonade stands. They both sold 300 cups of lemonade in a 30-day period, so they seem pretty similar. They both sold an average of 10 cups a day. On most days, Bill sold 10 cups. Jill never had a day when she sold 10 cups, even though that was her average. So take a look at their numbers and you'll note, Bill literally on most days sold 10 cups. There's a handful of days where he sold 9. There's a handful of days where he sold 11. On most days he sold 10. Conversely, Jill has a very high variance in her process. You see there's zeros, there's twos, there's ones, and then once in a while there's 150. And then some more ones and twos. There's seemingly no rhyme or reason. Tons of variance. So when we use that word variance, I want you to think of Jill and how one day she sells 1 and one day she sells 150 and the next day she sells 1 again. That is a great little summary of what we mean when we talk about variance. Averages. We're going to talk a bit about averages here as well. Most of us have a pretty good grasp on an average or a mean, M-E-A-N. It's a very general aspect of data. It's far more meaningful when you view it with the context of mode and variance. It's really a commonly misunderstood and misinterpreted number, the average is. And it's often mistakenly thought of as the mode or median, and that can lead to some very big mistakes on a large scale. Misuse of the average is a common mistake, especially during comparative analysis, and it can lead to really large-scale changes inappropriately. And we're going to take a look at an example of that. Alright, so we're going to tell a little fable about the evils of averages and comparative analysis. In our story, we have a company with a corporate office, you see here. They have reached out to their customers and come to the conclusion that cycle time is very important to their customers. And so they say to their two factories that, hey, the customers need faster cycle time. 8 days is too long. Our customers have told us that is an unacceptable amount of days to wait on this product to be delivered. So which of you two, you mean two factories, which of you has the best process? Who has the fastest average cycle time? So we have factory A and we have factory B. Factory A answers, hey, our average cycle time is 5.5 days, not too shabby. Factory B comes up, well, you know what, our average cycle time is 4.5 days. Clearly we have a better process here, we run a tight ship. So what management hears is, oh, Factory B usually gets the job done in 4.5 days. That's, about half of the time, our cutoff at 8 days. Good job, Factory B. Factory A, why don't you start replicating what Factory B does? Because most of the time they finish the job in 4.5 days. Unfortunately, that is wrong. No one said most of the time they finish the job in 4.5 days. They said that was their average cycle time. In fact, if you want to talk about most of the time it takes 8 days. Most of the units this factory is creating takes 8 days or more to deliver. On the other hand, Factory A, who just got their hand slapped, most of the time it takes 5 days. The most frequent number of days it takes to deliver their product is 5, and only 20% of those units take 8 or more days. So we're left kind of perplexed. How is this possible that Factory B has a lower average cycle time than Factory A, when most of the time it takes 8 days or more to complete their widget? How is this possible? Well, let's take a look at their histograms to get a more meaningful and knowledgeable understanding of their processes. First, let's talk about upper and lower specification levels. Based on the customer's feedback, we learned that most customers don't mind waiting 3 days for this product, but they start to be less satisfied when it takes 8 days or more. So this means that our lower specification limit is 3 days, and our upper specification limit is 7 days. So anywhere between 3 and 7 days is fine, according to the customer. If we deliver it faster than 3 days, that's great, but it's not really appreciated by our customers because for this product, they're typically not even ready to use it yet. If it takes more than 8 days, they start to get a little twitchy. So anywhere between 3 and 7 days, that's our control limit. That's what we should be shooting for. That's what's acceptable to our customer. Factory A and Factory B. Factory A, 70% are delivered within those specifications. Certainly room for improvement, but it is a lot better than Factory B, who we are recognizing as being the ones to shoot for. 0% are delivered within these specifications. A little more than half over on Factory B, a little more than half of them take 8 days, and the other half only take 2 days or less. So looking at the averages really oversimplified things. Management came to the conclusion that Factory B was the place to emulate, just because they had a lower average cycle time. But the fact is their performance is worse, and this confusion is really the result of variation in the process. So we're going to take a closer look at histograms for both Factory A and Factory B, and kind of see what the value is in having a histogram. As you can see, for Factory A, their average cycle time is 5.5 days, as we've demonstrated already. The most frequent number of days, that's the mode, the most frequent number of days it takes to deliver is 5. And only 20% of their work is outside of those specification limits. So when the mode, when the mode and the mean is average, it mean the same thing. But when the mode and the average are similar, that means there's very little variation. Their average cycle time is 5.5 days, and typically it takes 5 days to deliver. So your average and the most common result are very similar to each other. Meanwhile, in Factory B, yes, their average is 4.5. That is their mean, but they never had a single delivery that took 4.5 days. They just have two extremes. They have it only takes less than a day or so, and they have it takes 8 days. So we average those out, you get to 4.5. But the most frequent number is that it takes 8. So when the mode and the mean are not similar, as in this case, the mean is 4.5 and the mode is 8, there's a big difference between those two numbers. That means there's a lot of variation, there's a lot of variance in this process. So as you can see, Factory B has no work done in the Goldilocks zone. Factory A, the majority of their work is within the specification limits. So we take another look at these histograms, see what other observations we can make. As we said, Factory A is clearly the better factory. They have a better process despite having a slightly higher average delivery rate on their cycle time. If we wanted to use TrimCal as an acronym to find waste, we can take a look over to the left of the lower specification limit. Typically, if you're looking for waste over there, you're most likely to find the I, the O, and the W of TrimCal. That's inventory, overproduction, and waiting. So remember, on the left-hand side of this lower specification limit, this is where we're delivering super fast, faster than the customer even cares. So do we have resources tied up just waiting and doing nothing until a customer walks in and hands it to them right on the spot, even though they don't care for it yet? Do we have inventory sitting around? Are we overproducing? Are we jumping through hoops that the customer doesn't care about? Those typically things that you would find on the left-hand side of the specification limit. On the right-hand side of the upper specification limit, the types of waste you're likely to find are the T, R, M, and C from TrimCal. You're likely to have transportation, rework, motion, or complexity, some unnecessary things. RAMP is another good acronym to think of and look for types of waste. Reports, approvals, measures, and policies oftentimes can contribute to non-value added steps that cause longer cycle time. So remember, if you want to look, whatever it is that you're measuring, whether it's phone calls or widgets or claims being processed, if you look at these individual examples on the upper and lower end of the spectrum, keep these types of waste in mind. And SCAMPER, another great acronym for finding solutions to those problems. So down to Factory B, well, the first thing that jumps out at you is this is what's called a bimodal histogram because it has two humps. This is kind of an extreme version of it. Typically you'd at least see some smaller data points to the left and to the right of the humps, but regardless, you have these two big spikes. And what that normally implies is that there's actually two processes happening, whether we realize it or not. We may say, oh, this is just Factory B's process, but within Factory B, clearly there's two different things going on. This might be two different managers, or maybe shift managers that have different methods and different priorities. It could be the source of the orders are different. It could be something in a SIPOC on the sort of supplier and input piece, but there's a different process going on when you have all of your examples falling at extremes like this. They all take only less than a day or so, or they all take more than 8 days. There's something different about those. That's something that you will find with a bimodal hump like this. So again, one last look at this histogram. Again, there's a ton of valuable information you can gather and some observations you can make by looking at the shape of a histogram. To the far right of that USL, we know that we have customer loyalty at risk. To the far left of the LSL, there's profitability at risk. Tons of different types of waste that we can find, and there are a lot of different shapes that your data will come in. If you're interested in this topic and you think you can use this tool, check out part 2 because we really delve into the various shapes that your data might come in and have some good starting points on where to look and what to look for depending on the shape of your data. Alright, well, thanks for checking us out and we'll see you next time.